Alright class, today we are going to discuss and learn about logarithmic functions. So there's a couple things we need to be able to do. We need to be able to write functions in both logarithmic form and exponential form. So there's two things we need to know. We need to know, one, what's logarithmic form? Well, logarithmic form, we can write it as, or if it is written this way, y equals log base a of x. So we can do that if its exponential form is written in the following way. So to write y equals log base a of x in its exponential form, we would write it as x equals a to the power of y. So when you look at a logarithmic form equation, y equals log base a of some value, you're asking yourself, that little a, if you raise that to the power of y, what would x be? That's essentially what this is asking. So let's look at some examples. Here in example 1, in these examples, this first one, but we're going to look at a few of them, we are going to evaluate the logarithm at the given value. So the very first one we're going to look at in example 1, example 1a, we're going to be given the function f of x equals log base 2 of x, and we are going to evaluate this when x is equal to 32. So what that means is we have y equals log base 2 of 32. To solve this, what we're going to do is rewrite this in its exponential form. So we're wondering, 32, it's equal to 2 to the y power. Well, what power do we have to raise 2 to get 32? The answer is 5. If we multiply 2 by itself 5 times, we're going to get 32. And all I did is I kept multiplying 2 by itself. I did not write that down, but I multiplied 2 by itself until I got to 32. Let's look at another example. 1b. We're going to have the function f of x equals log base 3 of x, and x is 1. So that means we have y equals log base 3 of 1. If we rewrite that in exponential form, that's 1 is equal to 3 to the y power. Well, what power do we have to raise anything to get 1? The answer is 0. So one of the things we need to make sure we're strong with when we are doing these log problems is we need to make sure we understand exponent rules. So I've got two more that I want to look at before we move on. So this is still example 1, but now we're looking at C, where we're going to have the function f of x is equal to log base 4 of x, and we're going to look at this when x equals 2. So we're looking at y equals log base 4 of 2. Well, to solve this for y, we're going to put it in exponential form. So 2 is equal to 4 to the y. Well, what power do we have to raise 4 to get 2? Well, I know 2 is the square root of 4. And if I think back to Algebra 2, a rational exponent, in fact, not just Algebra 2, but just thinking back to some previous topics, if I want to find the square root of 4, I'm going to write this off to the side in another color. The square root of 4 is the same thing as 4 to the 1/2 power, which means if we're solving this logarithm problem, y is going to equal 1/2, because 4 to the 1/2 is the same as the square root of 4, which gives us 2. Alright, last one for example 1. We're going to look at the function f of x equals the log base 10 of x when x is 1 over 100. So we're looking for y equals log base 10 of 1 over 100. So now let's put it in exponential form. 1 over 100 is equal to 10 to the y power. Well, what do we have to raise y to get to 1/100th? So I do know that 100 is 10 squared. So I know 2 is going to be involved in my answer. 100 equals 10 squared. I also want us to keep in mind there is a rule that if we have a fraction, we can write that as a base to a negative exponent. For example, 10 to the negative 1 is the same as 1 over 10. So utilizing both of those ideas, knowing that 10 squared is 100 and anything raised to a negative exponent is 1 over something, I know that y is going to have to equal negative 2. Alright, I have some properties I want to give you. So some properties of logarithms. The first property pretty much says if I have the log base a, so the log of any base of 1, it's always going to equal 0. And that is because a to the power of 0 is equal to 1. And I've got 4 properties here. So my second one, if I have the log with the base of a, that's going to equal 1 because a to the first power is equal to a. If we were just rewriting these in their exponential form or going back and forth between exponential and logarithmic form, they work. Our third property, if we have log base a of a and now this a is raised to a power of x, our answer is going to be whatever the power is. And I don't have a because with this one, but I have an and. And if I have a raised to the power of log base a of x, it's going to equal x. And our last property of logarithms states if the log base a of x is equal to the log base a of y. So if you've got two logarithmic expressions with the same base, then x equals y. So let's look at a couple more examples. So example 2, we're going to evaluate the following. So we're going to look at 3 parts to this. We're going to have log base 4 of 1. We have to figure out what does that equal. We're going to have log base square root of 7 of the square root of 7. What does that equal? And lastly, we're going to look at 6 to the log of 6, log base 6, of 20. What does that equal? Okay, well, using the properties we just talked about, log base 4 of 1, that looks the most like that first property, log base a of 1. In this case, our answer is going to just be 0. If we have 1, it could be our base, but 1 is what we're looking at with the log. With whatever our base is, our solution should always be 0. In B, this also looks like one of our properties. It looks like the second property, where the base and what we're looking at are the same. If that happens, where this part and this part are the same, our answer is going to always be 1. C here looks like the second part of that third property, where we had a to the log of base a of x. So if these numbers right here are the same, our answer is just going to be whatever the power is. So our answer here is going to be 20. Not the power. It's going to be this portion right here. Okay, let's look at another example. So example 3. We are going to find the value of x to make each statement true. And I've got 3 parts to this one as well. So the first part, we are going to look at the log base 3 of x is equal to log base 3 of 12. So this is utilizing that fourth property we looked at. The logs have the same base, so we can just take what they have and set them equal to each other. We can say x equals 12. If we had more information in there, we would have had to do some more steps. This one was quick. We just need to know that x is 12. (3b), we're going to have the log of 2x plus 1 is equal to the log of 3x. And as a review from Algebra 2, if they don't give you the base number, that's called the common log, and that has a base of 10. Okay? So we have the same base, it's 10. We are going to write this as 2x plus 1 equals 3x, and we're going to solve this for x. So we need to subtract 2x. We're going to get 1 is equal to x. So we're done with that one. Alright, let's look at one more before we look at the natural log. So we're going to have log, part C here, log. I'm not going to have room to write it there, so let's look at one more page. So this is still example 3. This is just part C. We have the log base 4 of x squared plus 6 minus 6, is equal to the log base 4 of 10. So same base, we're going to set what's in the log equal to each other. We've got x squared minus 6 equals 10. So we are going to add 6 so we can solve this for x. So we're going to get x squared equals 16, and if we take the square root of both sides, we're going to find that x is equal to negative 4 and positive 4 because the square root has both a positive and negative answer. Alright, now let's take a look at what the natural log is. So the natural log. Alright, how we're going to define this. We are going to say if we have f of x and it's equal to the log and the base is e, the number e, which if you remember is about 2.7, it's an irrational number, it goes on forever, of x, instead of writing that, we can write that as ln of x, with an understanding that x is greater than 0. So let's look at some examples of natural logs. So example 4, we are going to evaluate using a calculator. Now I don't have a calculator I can show you on this screen, but I will talk you through what I'm doing. So we're going to say that our function is the natural log of x. And in our first part, we're going to say x is equal to 2. Now, on your calculator, there is a natural log button. It's found over by where the on button is. So if we push that button and have the natural log of 2, and then we hit enter, we're going to find that that is about 0.693. Now in class, I'll show you where this button is on the calculator. Let's look at 2 more. So we've done A, let's do B, where x is going to be 0.3. So again, we just use our calculator. We type in natural log of 0.3, hit enter. It's going to give us about negative 1.204. Now, in some cases, say they tell you you need to use a negative number. Well, if you remember back to our little bit of notes on natural log, x can't be less than 0. So if we were to type in the natural log of negative 1, you're going to just get an error message when you type that in, because it just doesn't work. So just like there's properties of logarithms, there's also properties of natural logs, and I want to give those to you. So properties of natural logarithms. Okay, so the first one, and again there's 4, and they're very similar to our last ones. If we have the natural log of 1, it's going to equal 0, and that's because e to the power of 0 is equal to 1. If we have the natural log of just e, that's going to equal 1, and that's because e to the 1 is equal to e. If we have the natural log of e to the x, that's going to equal x. And e raised to the power of the natural log of x is going to equal x. And lastly, we're not going to have any more examples after this. If the natural log of x equals the natural log of y, then x equals y. And that's going to wrap up our lesson.